Okay, everybody, good morning. Um, so last time we more or less finished that chapter 2 on series. This section 2.6 of power series, I didn't say anything about, and I'm not going to say anything about it at the moment. And we'll be returning to this. We'll return to this with the material on differentiation. When we're doing differential calculus, we'll return to the topic of power series. I mean, you might read through the section yourself at the moment anyway. Suffice to say for the moment that objects like this here, definition 2.5, these are called power series. Power series is the term we use when we're looking at a function that is defined by an infinite series. So there you see the infinite series has the variable x in it to various powers. Okay, so when you've got an infinite series that is really like an infinite polynomial in the variable x defining a function, then this kind of thing is called the power series. It's just a name attached to it. But they mainly arise in so-called Taylor series, where a reasonably well-behaved function can be expressed as a power series, like this one down here, and featured in the coefficients of the polynomial are various evaluations of various derivatives of the function f. So it's all about differentiation. So that's why I'm going to postpone the discussion of it till the later chapter on differentiation. So that allows us to move on to chapter 3 on functions. Okay. We quiet down a bit this chapter. So now I'm not claiming that nobody's heard of a function before. Okay, so of course we're well used to discussing and using functions. Okay, you've used them in lots of your mathematics up to now. We've been talking about this unit stats. I'm sure you're using functions left, right, center, all over the place without too much worry. But what we'd just like to do here in this chapter is establish some ways to talk about functions, establish some notation and terminology and a few different techniques that kind of are going to inform some of our later discussion about functions. Okay. So in definitions 3.1 and 3.2, we define the idea of a function. Okay. Very generally, as being a function f between two sets, x and y. So this kind of thing, a function from x to y, is a way of associating to each element the set x an element called f of x from the set y. Notice it's an element. So for any given little x, there's one element f of x in R. Now, I say a way, I mean, you can imagine just some completely random ad hoc way of associating, picking elements in this set, pairing them with elements in that set. In general, there'd be many, many ways to do that. I mean, most of the time we're going to be talking about mathematically meaningful ways, or ways that arise naturally from things in physics and engineering and so on. So some terminology and notation. X and Y are sets, okay? So X is the domain of f, is what we call it. The domain of the function f. Y is the codomain. And some other bits of terminology chucked around there. Yeah, the elements x from the set x are the arguments to the function. The domain, codomain, and the elements f of x, which live in y, are the values of the function. So, I mean, just to look at a couple of immediate examples. In example 3.1, see we introduce the function s, which goes from r plus to r. R plus means the set of positive real numbers. And this function s is defined by, well, for every x in R plus, s of x, we're going to define it as the square root. So it's this familiar operation to take the square root. So you've been using these upside down a's with me yet? No, you haven't seen the upside down a yet. Okay, I won't use it yet. For all. Upside down a means for all. Saeed will be introducing that as part of predicate logic. You see an upside down A meaning for all, and a backwards capital E, which means there exists. But I'll avoid using it for the moment. Notice we couldn't have, we couldn't have this square root function as s going from R to R, because there's no natural way what is the square root of -3? There is no real number such that when you square it, you get -3. So when you square a real number, the answer is always non-negative, greater than or equal to 0. So you couldn't have your square root function, something obeying this formula, this rule, set up with this codomain of all the real numbers. But we can have it if we restrict the codomain of s to the positive real numbers. I mean, over the other page, there's another example. Okay, the function you're familiar with, the sine function, that can be taken as going from the real numbers to, say, the closed interval -1 and 1. We might define it as like this, where sine of x is the, well, there's a number of ways to set it up, but you can set it up as sine of an angle is the vertical coordinate of the point of the unit circle where the radius with angle theta intersects the circle. So this value here is sine of theta. And there's a whole host, or It's a whole host and family of functions that collection of standard functions that you're familiar with and that you've been working with. And just another bit of terminology, definition 3.3. Some of this might conflict with terminology you've met before, but this is the terminology we're going to use in the course. So if we say the range or image of a function, so g, what am I saying here? G is a function from sets v to w. Then the image or the range of g is this set here, the set of all the values. So it's a subset of w. It might be all of w, but it isn't necessarily all of w. W, the codomain of G, is just the set where the values live, so to speak. The set containing all the values of G. Okay? But there may be other elements in W that do not occur as the value of the function. For instance, for example, with this square root function, going from r plus to r that we just saw, s of x equals the square root of x, then the image of s, which by definition is all the square roots such that x is in the domain of the function, this is just going to be r plus itself. So it's a proper subset of the codomain r of the function. So that example shows that with the feature that the codomain of the function s, the one on the right, there's a lot more elements in there than actually occur as values of the function. So remember, the place where the arguments are is called the domain. The place where the values end up is called the codomain. And this subset of the codomain, consisting specifically just of all the values of the function, we call that the image or sometimes the range of the function. Now, the next definition could well be new for you. You haven't seen it before. So there's a couple of terms here we're going to introduce which describe the way the function relates to its domain and codomain. So in definitions 3.4 and 3.5, we have these two terms. Okay? So definition 3.4 is this adjective injective. It's also known more informally as the property of one-to-one. So we can read the definition there. A function g from u to v is injective if and only if no two elements from the domain get mapped to the same element in the codomain. So you can best illustrate the injective property by showing non-injectivity. So non-injective behavior is where and we often use these kind of pictures when we want to describe aspects of behavior of a function. So if G is a function going from a set U to V, non-injective behavior is when, as part of the function, you've got two different elements, say a U1 and a U2, going to the same element little b. G of U1 equals V, G of U2. And as suggested by the diagram, these two arguments, these two inputs of the function are definitely different. This picture is an example of a mapping arrow picture. Okay, so this is one way to illustrate or depict the action of the function, drawing kind of Venn diagrams for the domain and the codomain, and indicating what the function is doing by arrows. Of course, you could have lots of other elements over here, lots of arrows coming out here, going various places in B. But if you have this kind of behavior, where you have two different elements, two or more different elements getting sent to the same element in the codomain, that's non-injective behavior. Non-injective behavior. So one way of kind of encoding the definition of injectivity is to say that G is injective if and only if the following condition holds for all pairs U1 and U2 from the domain. If it was true that G of U1 is equal to G of U2, really what that means is that, in fact, U1 and U2 aren't really two separate elements. We were just simply making the same element with two different labels. So this is not what's depicted in the diagram. The diagram is depicting non-injective behavior, where we do have two different elements that get sent to the same value. This statement here, I mean, in the notes, I'm using the upside down A for all of them here. This statement here is the definition of the term again. For every pair of elements in the domain, if G takes the same value on those two elements, it really means they weren't two separate elements, they were really the same element. So that's what's known as an injective function, or more informally, a one-to-one function. This is illustrating so-called two-to-one behavior. Because you've got two different elements going to one element. The next term, definition 3.5, is surjective, or known more informally as onto. And surjective is the property when your function, when every element in the codomain occurs as a value of the function. So again, with this kind of mapping diagram, you've got your domain and codomain of the function. If everything in here has an arrow coming into it, okay. If there are no lonely elements of the codomain that don't occur as values of the function, then it's surjective. So every element of the codomain B occurs as a value of G. Or another way of saying it, that the image of G, which when we defined it before, the image of G was just a subset of the codomain, if it's actually equal to all of the codomain. Okay, so that is a surjective function. I might also put a couple of double arrows coming in here. I mean, it might not necessarily be one-to-one. Could have multiple arrows coming into the same dot here. So a non-injective function, a non-surjective function, excuse me. This would appear as the domain and codomain of the function, where you might have elements with arrows coming in. Well, if this diagram was complete, if this mapping diagram was complete, if all the arrows were drawn in for the mapping of the elements from here, from the domain to the codomain, if this diagram is complete, this is a non-surjective function because there's at least one element there. There's at least one element in the codomain that does not occur as value. This diagram shows G is not surjective. As there is an element B, okay, this one up here, an element little b in the set B, and for all U in U, G of U is never B. So that's an example of non-surjective. Now these functions of one-to-one and onto, injectivity and surjectivity, they're two different properties. They're independent properties. Okay? So you can write down the definitions of functions that display all four possible combined behaviors: injective and surjective, injective and not surjective, not injective and surjective, and not injective and not surjective. So there's no strict relationship between the two properties. They're two independent properties in that sense. So let's look at another example. If we think of the sine function again. Now we're familiar with the graph of sine is the periodic oscillating signal. Looks something like this. Continues on there, so just plot in some points. 0, it reaches maximum values of 1 and -1, and it reaches a maximum there of pi over 2, it's back down to 0 over pi, 3 pi over 2, 2 pi, etc. Okay, so this is the graph of sine effects. But by restricting or extending its domains and codomains, you can make you can exhibit functions that are variously injective and not surjective. So for instance, this first example, f1, if we define f1 to go from the interval 0 to pi over 2 to the interval 0 to 1, so there you're just looking at the behavior of this function on this interval here between 0 and pi over 2, and we're declaring its domain as this subinterval of the vertical axis. Well, without just arguing from the graph. So f1 of t equals sine t. Just arguing from the graph, it's not a rigorous proof, but from the graph we will say that f1 is injective and surjective. Injective and surjective. It is never true that two different arguments in this interval, that two different arguments from the domain get sent to the same value. Okay? That never happens. Also, so that means it's injective. You never have two separate points in the domain getting sent to the same value in the code. The fact that it's surjective is because every value in the codomain, whichever value in the codomain you care to specify, there is always a corresponding value in the domain that gets mapped to that number. With every horizontal line here, chops the graph of the function over this interval in one point. So every value between 0 and 1 on the vertical axis occurs as a value of the function for some argument t between 0 and pi over 2. But so that's f, that's the sine function appearing as an injective and surjective function. However, if you set it up slightly differently, if we define a function f2, this time going from the longer interval 0 to pi to the larger interval 0 to 2, well, now what's it looking like? See, now we're mapping the whole of the interval 0 to pi. And our codomain we're taking to go all the way up to the value 2. So you see a number of features here. For some values of y for some values up here, on the vertical axis, there are two values in the codomain. There are two values in the domain that get sent to that value. So this is f2 of t, again defined as sine of t. And we can see that for any value of y in the interval 0 to 1, there will be two values. Label them here t1 and t2. Two values t1 and t2 in this extended interval 0 to pi, where f of t1 equals f of t2 equals y. So that's definitely not injective. Because you have two separate values in the domain getting mapped to the same value in the codomain. So this function f2 is certainly not injective. It's also not surjective, because if you go a bit higher and consider points up here, the sine function never reaches those heights. So there are values in the codomain of f2, there are values in the codomain of f2, maybe those values above 1, which never occur as values of the function. For any y inside the interval 1 to 2, there are no arguments. There are no arguments t where f of t equals y, as the sine function is bounded above by 1. Always. Part of the definition, just a feature of the way that sine is defined, it always takes value less than 1. So this f2 is neither surjective. So even with the same underlying process or underlying mathematical idea, by adjusting the domains and codomains, you can build functions that are maybe injective, maybe not, maybe surjective, maybe not. So these are properties that are sensitive to precisely what the domains and codomains are for the functions.
Is there a special name for when something's not surjective or injective?
When it's neither?
Yeah.
No. Not that I'm aware of. No. Badly behaved, maybe, or, but you know, it's not good. But there is a special term for when it's both. Okay, so when a function is injective and surjective, it is called bijective. Okay, so that's definition 3.6. But that's the only, as far as I'm aware, that's the only extra term applied to one of the four combinations. Bijective. So bijective functions would be considered well behaved, nice behavior. And this has a connection to the existence of inverses, which we'll discuss later. In order for a function to have an inverse, which we'll come on to later, we will see that it needs to be bijective. Now, so far this discussion has been quite abstract because we've just been talking about functions from some set to another set. Okay, the examples we've given are sine and square root functions from certain sets of real numbers to certain sets of real numbers. But those definitions, injective and surjective and so on, they apply to functions between n sets. But in section 3.1, we look at real functions, so-called real value functions. So these are functions f from x to y, where x and y are both subsets of the real numbers. So you're going from real numbers to real numbers. Maybe not all of the real numbers, but subsets of them. And in these cases, for such functions, the familiar arithmetic operations of addition and multiplication are subtraction and division we'll consider as being addition and multiplication under other as well. Okay, but these two fundamental arithmetic operations of addition and multiplication and R, these operations extend to these functions. For such functions, the familiar arithmetic operations of plus and multiplication extend to the functions themselves. So if we have functions, say two functions, f1 going from, I'll just call it f, just to stick with the notation. Let's say we have two functions, f, r to r, and g, r to r. Then we can add the functions together. We can take another real number lambda and we can multiply one of the functions by lambda. We can take the two functions and multiply them together. And under certain circumstances, we might even take the reciprocal of one of these functions. So what we've written down here are ways of combining functions. Okay? So it's very common in mathematics, and you need to adopt this way of thinking that a lot of the time we think of functions as objects in themselves. Okay? So the function, the way of mapping values, arguments to values, is regarded as an object in itself. Okay? And all of these combinations, adding functions together, multiplying functions together, multiplying functions by another real number, taking the reciprocal of a function, all of these have what we'll say is the obvious definition. Now, to define a function, you have to say what values it takes. Okay, you specify the domain of the codomain of the function, but really you specify what the values of the function are. And the value of the function f plus g, when you evaluate it at an argument x, is simply the value of f at x plus the value of g at x. And similarly, if you scalar multiply the function f by another real number lambda, the value it takes at an argument x is simply lambda multiplied by the value f of x. And the value that the product function takes at x, the obvious definition, f of x multiplied by g of x. And the value that the reciprocal function will take at x is the reciprocal of the value of f of x. But for this one, you need an extra condition provided f is never never zero valued. Sometimes f gives a value 0 as one of its values, then you'll run into trouble there because you'll be trying to divide 1 into, you're trying to divide 1 by 0, which doesn't make sense. Okay, so there's an extremely natural way in which we can take existing operations and use them, existing operations on R, and use them to define new operations on functions. On functions f and g, pairs of functions on real value functions. That kind of pattern, or that kind of way of taking existing things and using them to define new and related things, you'll spot many times in your study of mathematics. But this kind of stuff, you may well have been exposed and seen this kind of stuff before, but the definitions are extremely natural. So that's for real value functions. And back to general functions for a moment. An extremely important function operation is what's called composition. So what's the operation of composition? You can, if we have two functions, I'll stick with the notation fx to y, suppose we have two functions like this. Now these look like two general functions, except there's something special about the relationship. The codomain of f is the same as the domain of g. So the values of f live in the same set where g takes its arguments from. So this means that we're able to, what we say, compose these two functions. There is a new function. There's a new function written as g circle f, read as g composed with f, or alternatively g after f. So that's how we write it, g circle f. We read it as g composed with f, or g after f. And the definition of this function there's a lot of sibilant discussion and chatting going on. It travels very well both ways. The room is designed for you to hear me, but by side effect, I hear everybody else as well. So you just chat in a non-sibilant way. Okay, thank you. And so here's this new function defined by, written like this, g circle f, and it goes from the domain x to the codomain z. So the domain of f to the codomain z, and it's defined in an extremely natural way, defined by, for all elements x in the codomain, g after f, this new function, evaluated at x, is simply g of f of x. Okay, so you can see how kind of universal and all-encompassing it is, because it corresponds to doing g, or performing g, after doing f. So you first apply f to the argument x, and then because of the setup, the value f of x lives in the set y, and so the function g is available to apply to that argument and take it on to a value in z. Okay? So this is what we call composition of functions. So doing one thing after another. And this is an extremely important concept in mathematics. There are whole areas of mathematics which are really studying this situation. Group theory, which studies, in one way of thinking about it, studies symmetries of objects and the way that symmetries of objects combine to produce new symmetries. So symmetry of an object is some transformation of the space in which the object lives that leaves the object unchanged. As a whole, or still appearing as the same object. And these symmetries are combined by composing them. Okay? Because they're transformations of the space, so you can perform one after another. So there are whole areas of mathematics that study this. So we could look at some examples. Example 3.3. And these are all examples of real value functions. And real value functions can be composed often. And so here we've got two functions. Two real value functions, f of x being x squared minus 3, and g of x being 2x plus 3. So we can, now we're being a bit loose about what the domains and codomains are. Just consider them as subsets of the real numbers. But these two functions can be composed. So there will be new functions f after g and g after f. And we can discover their definitions by applying the definition of composition. The definition of this composition is f after g of x. And this is the other way around, g after f of x. So this is f of, well, g of x is 2x plus 3. F of x is x squared minus 3. So we want to apply f to 2x plus 3. How does f apply to an argument? It squares the argument and subtracts 3. So we have 2x plus 3, all of it squared, and we subtract 3. How does g apply to an argument? G applies to its argument x and gives you back 2 times the argument plus 3. So this will be 2 times x squared minus 3 plus 3. And what we discover when we expand these things out, so here you'll get 2x squared minus 6 plus 3, so you get 2x squared minus 3. Here you'll get 4x squared plus 12x plus 9 minus 3, so plus 6. So we see here that f after g is not the same as g after f. F after g is effectively the polynomial 4x squared plus 12x plus 6. That is certainly not equal to the polynomial 2x squared minus 3. In general, they have different values. They are certainly not equal as functions because for most arguments, most if not all arguments, they take different values. So this is the typical behavior. In general, composing functions, it makes a difference in what order you do the composition. The term for this is, in general, composition is not commutative. So, commutative is the technical term we give to an operation when it doesn't matter what order the arguments are. Okay? So addition of numbers is commutative because you have numbers and you're adding them. A plus B is always the same as B plus A. It doesn't make any difference what order you order the arguments to the function. But composition is not commutative. And this is no surprise. So I mean, I'm not saying that these two are always different. If the functions were defined in different ways, they might sometimes be the same, but it's special behavior. It's special, exceptional behavior when the composition of two functions is the same in both orders of composition. Okay? The typical or expected behavior is for them not to be the same. And that is not really a mathematical fact. It's not really something to do with real numbers. It's like a fundamental feature of reality. Because composition is doing one thing after another. And in general, when you perform transformations in sequence, in general they have different results depending on the order. And it's nothing to do with mathematics. It's like if you think about, say, baking a cake. Baking a cake, okay, there's two fundamental operations. You mix the ingredients, and you take the mixture and you bake it. And you get a nice cake. But if you separately take the ingredients, the flour, the butter, sugar, whatever, you separately bake the ingredients and then mix them, you don't get a cake. You get a mess of heated up ingredients. Okay? You certainly don't get a cake. So those fundamental operations, mixing and baking, you do it in the right order, you get a cake. You do it in the opposite order, you don't. And that's just a general feature of the way reality is set up. In general, performing actions in sequence, we'd expect them to lead to different results. There's something special about these transformations that means that their order can be changed. Okay? In general, if you're acting on the same elements, the functions, composing them, it's sensitive to the order in which you compose them. Okay, so that's the end of our introduction to this function chapter, or the start.